I'm back with another video, and this time we'll be working on this problem called combination sum 2. And I found it really interesting. It has a couple of ways to go about it, and today we'll be discussing one of the ways which I think is pretty straightforward, and I think it's the best for the interviews. So I think it will be really helpful for everyone doing it. Okay, so let's see. So the problem states that we have a bunch of candidates and we have a target that we need to achieve. And we need to find the number of combinations that we can have given those candidates such that we achieve the target. And the combination, the way we find the combination is that all the elements of the combination should the sum of those elements should equal target, right? So let's see the example, because that's the best way to understand it. So in the example, we can see one of the combinations is 116 that has been extracted out of the candidates, and the sum of the candidates is equal to 1 plus 1 plus 6 is equal to 8, right? And so on and so forth. What makes this problem a little challenging is this note that the solution set must not contain any duplicate combinations, right? Uh, Now, I know that when we read this kind of problem, sometimes the problem isn't that difficult. The extra constraints that the interviewer puts makes it a little more challenging. Now, I remember when I first solved this problem, I used a set, right? So let's say you have an algorithm that gets you all these things, right? But the issue is that those candidates will may contain duplicates, whatever your algorithm is. So the traditional approach is you, let's say, have x number of potential candidates, and then you use set to store those candidates, and then you just return the set, right? Oops, I'm not able to type today. Return the set. Now, the issue with this kind of approach is, I mean, it's a valid approach, but the thing is that you need to keep a set, and the set, whenever you add an element, or let's say whenever you add an element, it takes log n comparisons, right? So that is not good, because if you add 100 elements, then it leads to 100 log n comparisons. So it increases from that point of view. So a better approach is thinking about each candidate. So let's say, so now we found what's the limitations of having a set, right? Whenever we add an element. So for example, if we add, let's say, we add 0, 0, 1 to the set, and the set already has 100 elements, right? Then we add this potential candidate to the set, and again, it will lead to many more comparisons to get it added at the right place. How can we avoid that? Okay, how can we still return unique combinations without maintaining a set? So one approach is sort the candidates. Okay, now I will clarify what's the benefit of that. So let's say our candidates is this, okay, and we sort those candidates. So now we have 1, 1, 2, 5, 6, 7, 10. Okay, now what's the benefit of sorting it? So let's say you are actually, let's make it a little interesting. Let's add couple of 2's here. Okay, so let's say you are using one of your algorithms, you're backtracking, recursion, whatever, and this is your current candidate that you are considering. So let's say you have some value, let's say x, y, and now you are fighting for the third place, right? Which candidate, like out of all of these, what should I put on the third place so that the sum is equal to whatever the target value is. So let's say the target here is 8. Okay, so you're fighting for the third place and you are considering all these, right? So let's say you are currently, you visited the first and the second elements, you say I don't want to consider it for some reason. So now you are at this point, right? This element. Now since the element is sorted, you can see that all these 2's will be together, right? Now the third place can have only one of these 2's. Okay, the reason is, if you say, all right, I will put 2 here, and let's say it matches target is equal, you push it in your return element, whatever you want to return as a vector or list. Next, so you consider this 2, x plus y plus 2 is equal to 8, and you push it into the answer. Next time you consider this 2 in whatever backtracking or recursion, whatever you're doing, and now your algorithm says, okay, this x plus y plus 2 is also equal to 8. Then you say target is equal to 8 and push it, right? So this time we have considered these 2, and every time the target is equal to 8. In the next recursive loop, you will encounter this 2, and you can see my point, right? You will always have you will always have duplicates of the form xy2 and so on and so forth. So for example, in this algorithm, you will have 3 duplicates of xy2, and that's the problem. Oh, sorry, that's yeah, I mean, you can say it's one of the problems of our current approach if we do if we just follow the traditional approach. Now, an intelligent way to do it and to circumvent this problem is, you say, if I'm considering the third place, so let's delete this. Okay, let's delete it. Let's say till now your combination is x, y, and it's less than 8, so you are fighting for the third element. And when you see this 2, you say, okay, how many duplicates I have? So your current pointer points at 2, and you go forward till the next element is a different element than the current element. So when you encounter this 2, you will say, okay, how many duplicates this 2 has? So it will say it has a couple of duplicates, and the pointer will move forward till the next element is not a duplicate. And here, the element after 2, this 2 is 5, which is unique, which is not equal to 2. So it will say, okay, now we can try 2. Because now our pointer points at 2, so we skipped all those 2's that were giving us duplicates. Okay, now we are at this pointer, and it will try x plus y plus 2, and it will give us 8, and we will push this x plus y plus 2. In next iteration, the pointer will move forward to 5 because we have considered all these elements, right? So this is a trick to solve these kind of problems. If you want to avoid set, you need to sort it first, and that's how you group all the similar elements together. So I have the code with me here. Let's paste it. I just wanted to explain it first before. Okay, so let's forget about this function first, the DFS. I mean, it's not best name, but I'm just calling DFS. So I sort the candidates first. This is the vector that I will return as an answer. This is my template vector, which will contain the candidates that I will potentially add to answer. And I'm keeping track. I'm starting from the current index. I'm using a current index. The current index basically represents the so let's say these are my candidates. This is one of the candidates. Current index basically tells me I'm filling this entry. So 0 means I'm starting from this entry, 0th entry, and it will potentially move forward, and it's basically the entry that I am considering right now, or the index that I'm considering right now. Okay. And target is target. Let's look at DFS. That's more interesting. Okay, so DFS first, the base case is basically if target is equal to 0, I push back to temp and return. Okay, that's fine. This loop is the chunk of this code. Okay, as I told you, the smart way to avoid duplicates is if candidates of I is equal to candidates of I minus 1, that means actually I can just put here 1 1 2 2 2 and 8 9 whatever, right? So let's say I am at this 2. Okay, my current index is at this 2, and I say this entry is important, I not equal to current index, because then I am basically looking at my element that comes before me, right? So if I'm pointing to this 2, I add it to my temp. But if I'm at this 2, I will look what's the element behind me. It's also a 2, right? So I don't need to consider this 2. Then I will look at this 2 and I will say what's the element behind me. I will say it's again a 2. So no need to consider these elements. I already considered 2, and then it will move forward to 8 9 10. So this is what this line is doing. If I is not equal to current index, and if candidates of I is equal to candidates of I minus 1, that means the value of my current element is same as the value of as my previous element. That means that I have already considered my previous element somewhere down the recursive loop, so no need to consider it at right now. And that's why current index is important, because current index says let's say I have some value in my, so let's say my temp is 1 right now, it's 1, right? And I'm considering the second entry to fill on the second index, right? So that means my current index is 1. So if let's say index, actually, so I mean you should get the point, right? I'm filling for the first index, but it's the second element, and I say that and this line will basically help me, avoid those duplicates. And rest of it is straightforward. You do a depth first search, I mean basically backtracking, but yeah. So I hope this was helpful, and probably it could be one of the things in your arsenal to tackle interview problems. So hope you guys learned from it, hope you guys enjoyed it, and I'll see you next week. Thank you.